Evenly distributing endpoints on a sphere. I need an algorithm that can give me positions around a sphere for endpoints, less than 20, probably, that vaguely spreads them out. There's no need for perfection, but I just need it so none of them are bunched together. This question provided good code, but I couldn't find a way to make this uniform, as this seemed 100% randomized. This blog post recommended had two ways allowing input of number of points on the sphere, but the Sav and Cowlar's algorithm is exactly in pseudocode I could transcribe, and the code example I found contained Node K, which I couldn't see explained and ruined that possibility. The second blog example was the golden section spiral, which gave me strange, bunched up results, with no clear way to define a constant radius. This algorithm from this question seems like it could possibly work, but I can't piece together what's on that page into pseudocode or anything. A few other question threads I came across spoke of randomized uniform distribution, which adds a level of complexity I'm not concerned about. I apologize that this is such a silly question, but I wanted to show that I've truly looked hard and still come up short. So, what I'm looking for is simple pseudocode to evenly distribute endpoints around a unit sphere, that either returns in spherical or Cartesian coordinates. Even better if it can even distribute with a bit of randomization, think planets around a star, decently spread out, but with room for leeway.
In this example, code node K is just the kth node. You are generating an array endpoints and node K is the kth from 0 to n1. If that is all that is confusing you, hopefully you can use that now. In other words, K is an array of size n that is defined before the code fragment starts, and which contains a list of the points. Alternatively, building on the other answer here, and using Python. If you plot that, you'll see that the vertical spacing is larger near the poles so that each point is situated in about the same total area of space. Near the poles there's less space horizontally, so it gives more vertically. This isn't the same as all points having about the same distance to their neighbors, which is what I think your links are talking about, but it may be sufficient for what you want and improves on simply making a uniform lot/long grid.
The Fibonacci sphere algorithm is great for this. It is fast and gives results that at a glance will easily fool the human eye. You can see an example done with processing which will show the result over time as points are added. Here's another great interactive example made by a Gman. And here's a simple implementation in Python. "1,000 samples gives you this."
The golden spiral method. You said you couldn't get the golden spiral method to work, and that's a shame because it's really, really good. I would like to give you a complete understanding of it so that maybe you can understand how to keep this away from being bunched up. So here's a fast, non-random way to create a lattice that is approximately correct. As discussed above, no lattice will be perfect, but this may be good enough. It is compared to other methods, for example at bendwavy.org, but it just has a nice and pretty look as well as a guarantee about even spacing in the limit. Primer: sunflower spirals on the unit disk. To understand this algorithm, I first invite you to look at the 2D sunflower spiral algorithm. This is based on the fact that the most irrational number is the golden ratio, 1 plus sqrt5/2, and if one emits points by the approach stand at the center, turn a golden ratio of whole turns, then emit another point in that direction, one naturally constructs a spiral which, as you get to higher and higher numbers of points, nevertheless refuses to have well-defined bars that the points line up on. Note 1. The algorithm for even spacing on a disk is and it produces results that look like n equals 100 and n equals 1000. Spacing the points radially. The key strange thing is the formula R equals SQRT indices, num underscore PTS. How did I come to that one? Note 2. Well, I am using the square root here, because I want these to have even area spacing around the disk. That is the same as saying that in the limit of large N, I want a little region R plus Dr. Theta, Theta plus d theta, to contain a number of points proportional to its area, which is our Dr. d theta. Now if we pretend that we are talking about a random variable here, this has a straightforward interpretation as saying that the joint probability density for R, theta, is just CR for some constant C. Normalization on the unit disk would then force C equals 1/pi. Now let me introduce a trick. It comes from probability theory where it's known as sampling the inverse, CDF. Suppose you wanted to generate a random variable with a probability density, Fz, and you have a random variable U uniform 0, 1, just like comes out of random in most programming languages. How do you do this? First, turn your density into a cumulative distribution function or CDF, which we will call Fz. A CDF, remember, increases monotonically from 0 to 1 with derivative Fz. Then calculate the CDF's inverse function F1z. You will find that Z equals F1U is distributed according to the target density. Note 3. Now the golden ratio spiral trick spaces the points out in a nicely even pattern for theta, so let's integrate that out. For the unit disk we are left with Fr equals R2. So the inverse function is F1U equals U1/2, and therefore we would generate random points on the disk in polar coordinates with R equals SQRT random, theta equals 2pi random. Now instead of randomly sampling this inverse function, we're uniformly sampling it, and the nice thing about uniform sampling is that our results about how points are spread out in the limit of large N will behave as if we had randomly sampled it. This combination is the trick. Instead of random we use arrange 0, num underscore PTS, type equals float, plus 0.5/num underscore PTS, so that, say, if we want to sample 10 points they are equals 0.05, 0.15, 0.25, ... 0.95. We uniformly sample R to get equal area spacing, and we use the sunflower increment to avoid awful bars of points in the output. Now doing the sunflower on a sphere. The changes that we need to make to dot the sphere with points merely involve switching out the polar coordinates for spherical coordinates. The radial coordinate, of course, doesn't enter into this because we're on a unit sphere. To keep things a little more consistent here, Even though I was trained as a physicist, I use mathematicians. Coordinates where 0 less than or equal to phi less than or equal to pi is latitude coming down from the pole, and 0 less than or equal to theta less than or equal to 2 pi is longitude. So the difference from above is that we are basically replacing the variable r with phi. Our area element, which was our Dr. d theta, now becomes the not much more complicated sin phi, d phi d theta. So our joint density for uniform spacing is sin phi slash 4 pi. Integrating out theta, we find f phi equals sin phi slash 2, thus f phi equals 1 minus cosine phi slash 2. Inverting this, we can see that a uniform random variable would look like acos 1 to 2u. But we sample uniformly instead of randomly, so we instead use phi k equals acos 1 minus 2, k plus 0.5 slash n. And the rest of the algorithm is just projecting this onto the x, y, and z coordinates. Again, for n equals 100 and n equals 1000, the results look like. Further research. I wanted to give a shout out to Martin Roberts' blog. Note that above I created an offset of my indices by adding 0.5 to each index. This was just visually appealing to me, but it turns out that the choice of offset matters a lot, and is not constant over the interval and can mean getting as much as 8% better accuracy in packing if chosen correctly. There should also be a way to get his R2 sequence to cover a sphere, and it would be interesting to see if this also produced a nice even covering, perhaps as is but perhaps needing to be, say, taken from only a half of the unit square cut diagonally, or so and stretched around to get a circle. Notes. Those bars are formed by rational approximations to a number, and the best rational approximations to a number come from its continued fraction expression, z plus 1 slash n underscore 1 plus 1 slash n underscore 2 plus 1 slash n underscore 3 plus ... where z is an integer and n underscore 1, n underscore 2, n underscore 3, ... is either a finite or infinite sequence of positive integers. Since the fraction part 1 slash ... is always between 0 and 1, a large integer in the continued fraction allows for a particularly good rational approximation, 1 divided by something between 100 and 100, and 1 is better than 1 divided by something between 1 and 2. The most irrational number is therefore the one which is 1 plus 1 slash 1 plus 1 slash 1 plus ... and has no particularly good rational approximations. One can solve phi equals 1 plus 1 slash phi by multiplying through by phi to get the formula for the golden ratio. For folks who are not so familiar with NumPy, all of the functions are vectorized, so that sqrt array is the same as what other languages might write map sqrt array. So this is a component by component sqrt application. The same also holds for division by a scalar or addition with scalars. Those apply to all components in parallel. The proof is simple once you know that this is the result. If you ask what's the probability that z is lower than z plus dz, this is the same as asking what's the probability that z is lower than f1u is lower than z plus dz. Apply f to all three expressions, noting that it is a monotonically increasing function. Hence fz is lower than u is lower than fz plus dz. Expand the right hand side out to find fz plus fz dz, and since u is uniform, this probability is just fz dz as promised.
This is known as packing points on a sphere, and there is no known, general, perfect solution. However, there are plenty of imperfect solutions. The three most popular seem to be: create a simulation. Treat each point as an electron constrained to a sphere, then run a simulation for a certain number of steps. The electron's repulsion will naturally tend the system to a more stable state, where the points are about as far away from each other as they can get. Hypercube rejection. This fancy-sounding method is actually really simple. You uniformly choose points, much more than n of them, inside of the cube surrounding the sphere, then reject the points outside of the sphere. Treat the remaining points as vectors, and normalize them. These are your samples. Choose n of them using some method, randomly, greedy, etc. Spiral approximations. You trace a spiral around a sphere, and evenly distribute the points around the spiral. Because of the mathematics involved, these are more complicated to understand than the simulation, but much faster, and probably involving less code. The most popular seems to be by Saf et al. A lot more information about this problem can be found here.
If you're on 2 theory, please consider subscribing.